Hey folks, Ms. Gosling here. In this video, we're going to be talking about Coulombs Law. And by the end of this video, you will be able to use Coulombs Law to solve electrostatic problems. So let's go ahead and start by talking about the equation for Coulombs Law. So we use Coulombs Law to determine the force between two charges, otherwise known as the electrostatic force, which I'm going to just write as the electric force. And so what we can say is that the electrostatic force, F sub E, is equal to K, which is our Coulomb constant. So K is a constant, and is equal to 9 times 10 to the 9th newtons times meters squared over Coulomb squared. So again, our force is equal to a constant times the product of the charges on each of our two charged objects. So Q1 and Q2 are the charges respectively on object 1 and object 2, so the charges on each object. And we're going to measure that in coulombs. So we're going to write that capital C, so you guys remember that the units for charge are coulomb. And we're going to divide that by r squared, where r is the distance between object 1 and object 2. So the distance between the two objects. So there you have it, guys. The electrostatic force between two objects is equal to KQQ over r squared. And I'm hoping that this equation is actually somewhat familiar to you, because it is similar in form to another equation that we've used to determine force, which is, of course, our gravitational force equation. F sub G is equal to G times M1 times M2 over r squared. So what we can see is some of the similarities and differences between gravity and electricity. Both of these two forces are dependent on a constant. Both are dependent on the distance between your two masses or your two charges. But what we can see is that gravity involves mass, while electricity involves charge. So again, our gravitational force and electrical force are very, very similar. And so hopefully solving Coulomb's law problems will be somewhat straightforward because you're used to using our gravitational force equation. So with that being said, let's go ahead and start with a problem. So what I have here is I have two positive charges, one with a charge of 3 coulombs and one with a charge of 4 coulombs, and they are separated by a distance of 10 meters. And so I'm going to go ahead and use my guess method to walk through this problem. So let's start with our givens. And in my problem, I know that Q1 is equal to 3 coulombs, and I'm going to say this guy is Q1, and this guy is Q2. We know that Q2 is equal to 4 coulombs, and we know the distance between them, r, is 10 meters. And my unknown for this problem, what I'm trying to find, is the electrostatic force, Fe, between my two charges. And also just to note, going back to this distance, I know I drew this vector from the edges of the two, but actually we're measuring our 10 meters from the center of our 2-point charges, which was hard to draw because they're giant red and black circles. Anyway, moving forward, let's go ahead and talk about the equation we're going to use. So the equation is, of course, going to be Coulomb's law. Fe equals K Q1 Q2 over r squared. And I'm going to go ahead and just substitute in my numbers in my sub and solve step. So my electrostatic force is equal to K, so 9 times 10 to the 9th, times Q1, or 3 coulombs, and also multiplied by Q2, 4 coulombs, divided by r squared, so divided by 10 squared. When I stick that in a calculator, that gives me Fe equals 1.08 times 10 to the 11th, divided by 100. or Fe equals 1.08 times 10 to the 9th. So there's one thing I still haven't talked about yet, and that is the direction of our charge, or direction of our force. So remember, our force is always a vector, so we have to have a direction. And in this case, because I have two positive charges, the direction of my force is going to be away from each other. So the force of Q1 on Q2 is going to be to the right, while the force of Q2 on Q1 will be to the left. So let's look at a problem with the same numbers, but opposite directions. So what I have here is I have a charge of 3 coulombs and a charge of negative 4 coulombs, separated by a distance of 10 meters. So what I'm going to do is I'm going to go ahead and start by drawing the field lines around my positive charge. And to do that, I'm going to go ahead and just draw a smaller version of this. So I'll draw my positive charge as this little red plus sign, and my field lines in a circle, and my field lines are going to be going away from my charge. So at the point where my negative charge is, which is again going to be a little negative side in a circle, my field lines are going to the right. However, what I have is I have this negative sign on my charge, which is going to flip the direction of our force. So while the field line for that positive charge is going to the right, the force that electron is going to feel is going to be to the left. So the force of Q1, my positive charge, on Q2 is going to have the same value as that previous force that we found. So 1.08 times 10 to the 9th newtons. But our direction is going to be flipped from our previous situation. So while in the previous example, our proton, our positive charge was pushed to the right, in this situation, our negative charge is going to be pulled to the left. So our direction is the thing that is going to be flipped. So I would suggest when you are solving these problems, ignore the sign on the charge until you are drawing your field line pictures, and you're going to just use the signs on your different charges to determine the direction in which your charge will move. Okay, so our takeaways for this. So first of all, we can use Coulombs Law to find the force between charges. Second, the direction of that force is going to depend on the sign of each of your charges. And one takeaway that I didn't mention, but that you will want to think about, is how you can use field lines to help you solve Coulombs Law problems.